Okay, hi BC Calc. So I want you to take out those notes that you had on series. I think the top sheet had arithmetic and geometric series, and this is the back sheet. And I want to start off as we kind of get into now the formal infinite series topics, is these 2 points above. When it comes to infinite series, the critical question for us is not necessarily what value the converging series converges to. So, in other words, if you look back at your notes from the first page, you remember that a geometric series converges if r is between -1 and 1. And for those geometric series, we're actually able to find the convergent value. The same was also true for the telescoping series on the previous homework. So sometimes there will be infinite series that not only converge, but you can actually find the value it converges to. But really, the critical question that we ask in our work with series really is just, does the series converge? What the series converges to, like what that infinite sum actually equals, really is not of much interest or use to us in our work tonight, and also to be honest, in our work with the calculus of this that we have not yet done, which won't be about for another 2 weeks or so. Okay, so when it comes to the calculus of infinite series in our work tonight, the question really is just, does the series converge or not? That's really the question. And so now we begin our study of what are called convergence tests. Now notice here a word that I think the whole thing I see is highlighted, but I want you to understand something. Tests for convergence of infinite series. Obviously, if a series is finite, every series that is finite will always converge, because if a series is finite, that means it actually ends. And if the series ends, that means it actually equals a sum, and so therefore it converges. So that hopefully is obvious, and if it's not obvious, maybe you'll make notes here to that effect. So essentially what we're talking about here are convergence tests. There are 8 in total, and just like methods of integration, what's difficult is not necessarily when you learn an individual convergence test. What gets difficult is when you have all 8 of them, or even all 4 or 5 of them at your disposal, and you have to choose which is the best convergence test to use. You'll start doing that a little bit tonight, but luckily tonight all I'm doing is showing you 3 convergence tests, one of which you already know. So the first convergence test, or the test for whether an infinite series converges, is the geometric series test. Okay, given an infinite geometric series, as you know already, an infinite geometric series will converge if r is between 1 and -1. Okay, so that's a nice way to begin, having one convergence test that's already obvious to you. And once again, side note here is that we happen to note that in this case, if the series converges, we actually can find, because we have that nice little formula, we actually can find what that convergent value is. But like I said above, that won't necessarily be the critical question. Okay, the second test that's new to you is called the divergence test. The divergence test states the following. Let me write it down for you first and we'll talk about it. Okay, here is what it says. Let's write this down first. Given an infinite series, look at this notation here. Given an infinite series, how do you know it's infinite? Well, the upper limit of summation is infinity, okay? Given this infinite series, and look what I have here as the summed. The summed is just standing in for whatever the expression for the, kth term is. A sub k, it could be maybe an arithmetic, it could be geometric. It also could be neither of the two, right? Given some series that's infinite, if, and look at this right here, if the limit as k approaches infinity of a sub k does not equal 0. Some people like to say, oh, basically are we saying like the infinitieth term in this series, or the quote-unquote last term of the series? If the last term of this series is not 0, right? So if the limit as k approaches positive infinity of a sub k, if the quote-unquote last term is not 0, then, whoa, what's going on? Then the series diverges. Okay? A really important point about the divergence test is the following. This is not at all saying the following, okay? A lot of people like to say, well, if the infinitieth term doesn't equal 0, we know the series diverges. Does that mean that if the infinitieth term equals 0, then the series converges? Is that true? And the answer to that question is not necessarily, okay? Let's write that down together. Notice, this is very important. If the limit as k approaches positive infinity of a sub k equals 0, this test is inconclusive. Okay, which means further investigation is needed. So let's just talk about this for a second. Some of you may be saying, but wait a minute, for a geometric series, right, for a geometric series, if r is between -1 and 1, then this limit will equal 0. And we know that for a geometric series, in that case, the series would converge. And you are absolutely right. But this is talking about series. If the infinitieth term equals 0, this test is not saying that the series will diverge. What this test is saying is further investigation needs to happen. Let's say this is the case, but you also notice that the series is geometric. Well, then in that case, you know that the series will converge. But there's a very famous series. It's called the harmonic series. It looks like this. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus ... okay? And let's just talk about expressing this infinite series using summation notation. The summation from k equals 1 to positive infinity of 1 over k. All right? Go ahead and make a note to yourself that this series, as you can tell by inspection, hopefully, it's not arithmetic and it's not geometric. And there are many reasons why this series is so famous. And we'll talk about one of them in about 30 seconds here. But this series is called the harmonic series. Okay, 1 plus 1/2 plus 1/3 plus 1/4. This is the harmonic series. And if you are looking at your convergence test that we have in our pocket, we only have 2 so far. We know how to test a geometric series. We have the divergence test. Well, it's not a geometric series, so I obviously can't even think about the geometric series test. Let's try the divergence test. Let's take the limit as k approaches positive infinity of a sub k, it's 1 over k. This equals 0, okay? This does not necessarily mean that this series will converge or diverge, but the point is that the divergence test is inconclusive. Right? So the question is, what does the harmonic series do? Does it converge? Does it diverge? I want you to think about it for a second. I mean, one could make the argument that by inspection, if you're adding 1/6, 1/7, ... 1 100th, 1 101st, ... 1 10,000th, one can make the argument that the terms start getting so small as to become inconsequential. Part of you, I'm sure, makes you want to say, oh, this series has to converge. Well, let's see. So the divergence test is inconclusive. The geometric series test, the test for whether or not a series is geometric, we can't even use that because there is no r. The series isn't geometric. Let's see if we have another test at our disposal. Let's try the integral test. The integral test says the following. Okay, the integral test says the following. Given an infinite series, look at this little side note right here. Rewrite a sub k as a function of x. Okay, so, and I'll show you how this works in a second. You're going to let a sub k be some function of x, and then what you're going to do is evaluate the corresponding improper integral. However the improper integral behaves is how the infinite series behaves. So this may look confusing, but just look what I said here. If you have an infinite series, by evaluating the corresponding improper integral, it will behave just like the infinite series does. So if the improper integral diverges, so does the series. If the improper integral converges, so does the infinite series. So let's take a look at that series from above, the harmonic series, and let's try and apply the integral test. So the harmonic series was asking to determine whether this series right here converges or diverges. Okay, what does it do? All right, well, here's what we're going to do. We're going to use the integral test. We're going to let f of x be the integrand in terms of x, and we're going to evaluate the corresponding improper integral. The definite integral from 1 to positive infinity of 1 over x dx. Okay, go ahead and do this. This is old news for you, and then replay me for the rest. Okay, so here is me doing the work right here for the improper integral. You have to rewrite as a limit. Look at my notation here, being very careful. Here is the limit evaluating. Here is me taking it all the way through. I notice that the improper integral approaches positive infinity, so the original series in question diverges by the integral test. Okay, so there you have it. That's just the information part of this screencast. There you have it. You have 3 tests for convergence: the divergence test, the integral test, and the test if it's a geometric series. Here's what I recommend when we're using these 3 tests, and some of this will not change. Okay, you now have 3 convergence tests. Here's what's very helpful. When you are asked to determine whether a series converges or diverges, here's what you do first. First and foremost, whoa, here we go. First and foremost, apply the divergence test. Why do you do that first? Because it's easy to do. You can almost do it mentally without writing anything down. Apply the divergence test, because if you apply the divergence test, if the limit does not equal 0, your work is over. You know the series diverges. Step 2, check and see if the series is geometric. If the series is geometric, then see if r is between -1 and 1. Just like last night's homework, however, you know sometimes that when you're looking at a series in summation notation, it may not be obvious to you that the series is geometric. In that case, just write a few terms out. After you write 1, 2, 3 terms, you can usually see quite obviously whether a series is geometric or not. Finally, step 3, use the integral test. Okay? For the homework you have over the weekend, and I say over the weekend because I don't see you tomorrow, you only have 3 convergence tests. So as you work through this triage of steps, with the homework you have tonight, working through step 1, 2, 3 in this order will allow you to reach a conclusion for the series of tests, for the series you have over the weekend. What I'm going to do right now is pull up the page in your book that this homework is going to be on, so we can work a few together. Okay, so here we are. Let's take a look at these. This is just taken right from your textbook, okay? Let's go ahead and do 18 together. Let's go ahead and do 16, and let's go ahead and do, oh, I don't know. Let's see, let's do 12. How about that? Okay, you go ahead and try them on your own, and then replay me for the answers, please. Okay, here they are. Here's number 12, and here's how I showed the workout. So here's the series. I first applied the divergence test. The divergence test yielded me an inconclusive result. I then checked to see if the series is geometric. Notice here the series is geometric. R is 1 over root e, and 1 over root e, that value of r, is in fact between -1 and 1, so the series converges. Here's 18, And if you look here, this is a great example of one where you're using the divergence test pays off. The infinitieth term, so to speak, approaches a non-zero number, so we know the series has to diverge by divergence test. Number 16, here's the original series. The divergence test is inconclusive. The series is not geometric, so the only way to determine this series behavior is to use the integral test. Okay, which I didn't do because I wanted to make sure I get this loaded up for you all. I'm going to put homework on the teacher page. It's going to be drawn from this page right up here, and I will see you on Monday. All right, goodbye.